And one last slide, I think, while we're on the plot scale here. This is now that same, well, this is another site, but this is showing now matrix potential changes. So these are tensiometers. These are porous cup devices that measure suction or matrix potential, and they're installed at 18, 30, 98, and 82 centimeters down through the profile. And this is their response to this wetting that occurred from 0 to 70 minutes here. And what we're seeing is some expression of preferential flow in the matrix potentials that we've recorded. So here at 18 centimeters, it's the first tensiometer to detect a wetting front moving down. Then we see the 30 centimeter rod detecting this wetting front moving down. Both of these come up close to saturation because at matrix potential of 0 kilopascals, these are saying that these particular tensiometers at these depths are saturated. And then some time away from that, we get responses now at depth. And what this is suggesting is that we're getting a slug of water kind of making its way down to 30 centimeters that's affecting this kind of response. And then another parcel of water that seems to be making its way deeper into the profile that's affecting this response. Again, in an equilibrium, Darcy-Richards-like way, we would expect this nice kind of cascading wetting front moving through the system. This is indicating that things are very non-equilibrium and that this idea of preferential flow is really influencing the behavior. So to summarize this plot scale, whether we're looking at a forest soil and really seeing what makes up this soil, something that we rarely look at, or we're looking at maybe a valley bottom setting where voles and moles are operating, or whether we're looking at a perfectly homogeneous sand, preferential flow is ubiquitous. Preferential flow is something that we see in all media, and it's something that we rarely acknowledge. And in runoff generation, it's really important for how we might turn on the hydrology of our hill slopes. So this is the segue now into the next section, which is the hill slope hydrology, hill slope scale. And at the hill slope scale, what we're going to try to do is take this understanding now of vertical infiltration and think about how this influences the transition to lateral flow. That's why we wanted to start off at the plot scale. How does this transient saturation develop at an interface? How does this process called transmissivity feedback work? I'll talk about this a little bit. This is very characteristic of till-mantled terrain. And then lateral preferential flow. How does it operate? This is another important driver of how hill slopes deliver water and solutes to stream channels. So we've talked about these depth declines in matrix and preferential kind of components of at the plot scale, things like vertical hydraulic conductivity, percent saturation, where maybe we're creating a zone of temporary saturation. But in terms of looking at the transition from vertical to lateral, we really go from a totally vertical component to flow to, at this zone, a significant lateral component. So even if we're on a steep hill slope, the unsaturated zone is dominated largely by vertical flow. Lateral flow in the unsaturated zone is very rare in terms of the tensiometer and other soil physics evidence that's out there. It's really happening where we get a zone, could be a contact between two different permeability layers, it could be a soil bedrock interface, it could be a soil argillic horizon interface. It's this kind of zone, and I mean this could be quite affected by the depth of the soil, the amount of storage one has available. Think of a 1 meter soil profile at 50% porosity within, say, 10% of saturation prior to an event. You've got 350 roughly millimeters of water in that soil profile, and you're adding maybe an inch of rain, 25 millimeters of rain. How does that rain move to depth, mix, and create lateral flow? It's affected by rain intensity, rain amount, hydraulic conductivity, soil depth, and this is something that we'll begin to look at. And again, one could have maybe two contrasting soil layers in terms of their lateral hydraulic conductivity. Remember some of the issues of anisotropy that we talked about, where we're more conductive often in forest soils in the lateral than we are in the vertical. This is what we're going to look at now for this next section. So let's take an example. Here's a hill slope. This one's in the southern Piedmont. Here's the soil surface. You can see it's fairly planar, but there's a hint of a depression here. And this is the bedrock surface. This is, on average, it's 0.63 meters, so pretty thin soil, but there are deeper pockets of almost 2 meters and some really thin areas where it's just exposed at the surface, the bedrock. And what we've done is ripped a trench along the base of the hill slope. This is much like a logging road along a contour, but in this case we're down to bedrock, so we don't have any underflow at this trench site. And what we want to do is begin to think about what are the controls on the lateral flow, this conversion from vertical to lateral at the hill slope scale. Is it all explained by surface topography, or given what we've learned, how does the underlying surface influence this? This is something that we've been doing at various sites. This is, one of my colleagues calls this technique Frankenstein hydrology, because it's really pretty grim what we do to some of these hill slopes. But the objective is to expose a trench down to bedrock and then capture at different sections maybe what the flow might be moving laterally, route that into a tipping bucket device like here, and then measure its chemistry and its isotopic composition as well. But the objective is to try to understand what turns on hill slopes. Why are hill slopes sometimes communicating large amounts of water to a road cut or a riparian zone or a stream, and why are some hill slopes unresponsive? So we're going to look at this example, the one in the southern Piedmont. So I'm going to show you data from along this trenched hill slope. It's about 25 meters long, and each of these sections are about 2 meters wide. But this is kind of a photo of some of these different sites. So from that hill slope topography, we can compute this topographic index. Remember, A is the upslope area, beta is the local slope angle. So we're taking this hill slope that's about 25 meters by, or 20 meters by 50 meters roughly, and this is what the topographic index would look like based on that high resolution DEM of the soil surface. Meaning that this would be the wet spot, and if we kind of use this as a surrogate for flow path, which is what we've talked about in the earlier part of this short course. Water flows downhill. It flows downhill in steep terrain because elevational potential is the main component of total potential. That's why we say water flows downhill. And this is kind of like the way to quantify that. So here we're saying that water flows downhill based on surface topography. Here we're saying water flows downhill based on bedrock topography. You remember those surfaces were really quite different. We had a fairly planar, smooth topographic surface and a kind of a crinkly, different looking subsurface. Well, this is what the flow paths would indicate based on the subsurface. And if we look at a distribution of flow paths or flow along the base of the hill slope, if we believe that water flows down slope based on that underlying topography, the flow would be distributed like this, and if we believe it is related to the surface topography, it would be much more uniform along the base of the slope. But think of this as a forest road intercepting flow from a hill slope. And these are some of the data that we find. This is distance along the trench, so from that left-hand side of the trench to the right-hand side of the trench. This is just that topographic index information I showed on the previous slide. So this top panel is just showing the surface topography and then the bedrock topography. And now this is showing the flow distribution, both in terms of peak flow and total runoff volume. Now looking at this in a kind of a very qualitative way, basically it's saying that most of the flow is coming out over here, both in terms of total flow and in terms of peak flow. And this is where the distribution of the bedrock topography would be indicating most of the flow would be emanating from. The surface topography is saying that the flow should be much more evenly distributed along the trench face, with most of the flow at that bedrock, or that topographic depression over here. So these data are indicating, and more data from different trench sites are saying, that at the hill slope scale, it's not the surface topography, it's the underlying topography. It's what we learned at the plot scale. Water moves to depth, backs up at an impeding horizon, and then it's exploiting that underlying surface to move laterally downslope. That's what these data are saying. So let's look at it a different way. Here's that same hill slope, and now I'm going to show you different rain events. These red dots are wells that we've installed on this hill slope. They're not all recording wells, they're maximum rise wells. So all I'm showing you is whether or not we detected any of that saturation on the hill slope for an event. So here's a 5 millimeter event, and for this event, these were the only wells that showed any detectable saturation. Now we'll just skip through a number of different events. Here's a 9 millimeter event. Now we've got these pockets of, yeah, question? Yeah, sorry, yeah, we're now looking down on the hill slope. Yeah, I'm sorry. We're looking down on the hill slope, that's right. But, you know, it's interesting that when you think of the kind of percolation-like aspects vertically and laterally, it's striking how similar they are, and we'll talk about that maybe at the end of the class. So we're looking down on the slope, the trench is along here, this is kind of moving in an upslope direction, right? We're looking down on it, and I'm showing you now the spatial pattern of water table development on the slope. 16 millimeters, I'm increasing in storm size, but we're not moving sequentially through the hydrologic year necessarily. 29, 50. Now you notice that up until now, we've had no saturated area. This is subsurface saturated area. There's no surface saturation here. We're just detecting water table down at that soil bedrock interface. But up until 50 millimeters, nothing is connected to the trench. Meaning that we can have events of 0 to 50 millimeters, and we produce, that hill slope is unreactive from the point of view of generating lateral flow at the trench face. Now we get past a certain threshold. In this case, for this hill slope, for these soils, it's about 60 millimeters. Here's a bigger event, 61 millimeters. Now we've connected this transient saturation. And that is when the hill slope is turned on. So here's kind of an, cycling through these things that we've just looked at. This is showing how this network of saturation might accumulate. This is very characteristic of hill slopes generally that are known to produce subsurface storm flow. The idea is that if this is the total flow from our hill slope at our road cut, at our trenched site, and each of these dots represents different rain events, this site is suggesting that you need in excess of 50 millimeters of rainfall if you're going to generate any lateral flow from this hill slope. Events smaller than that, it'll just be stored in some fashion, some distributed fashion in the slope. And that once you exceed this threshold, that rainfall and runoff are correlated. It's affected a little bit by antecedent wetness, but not so much in the sense that, well, here is a little bit, but there's some effect of antecedent wetness, but this we'd say is a secondary effect after total precipitation. Yeah, that's a good question. Let me skip ahead here. Here are 4 of those other sites that we looked at. And this is the site that we've just been focusing on, this site in the southern Piedmont. This is total flow. This is storm precipitation. Here's one in New Zealand at the Mai catchment. It's showing that after about 18 millimeters of rain, boom, we turn it on. And that after that, now I'm not showing all the dots here, so it's not as simple as I'm making out to be, but it's suggesting that that threshold is something like that, and the slope of the line of the data that we do have looks something like this. Here's one of our sites in Japan. Here's the H.J. Andrews Forest in western Oregon, and now here's the Panola site. It's suggesting that this threshold behavior is kind of like an emergent property of hill slopes. And it really comes down to how saturation is detected on the hill slope, or generated, I should say, and whether or not that patchy saturation connects laterally to turn on and excite the hill slope. And it's driven by stuff at the plot scale, but we're saying we can't take a soil core and say somehow we can accumulate, a billion of them and say that's how a catchment works. The catchment is really more like a series of kind of cryptic units that connect and disconnect in these threshold-like ways. Now, for events less than this at these catchments, runoff would be generated in the stream channel, but all of it would be derived from the near stream zone. Saturation overland flow, saturation excess overland flow, the riparian zone, the riparian groundwater would be feeding the stream channel. It's after this threshold now that we've activated the other parts of the watershed. Questions? Yeah.
Do you find this relationship regardless of vegetation?
Well, the data to generate these relationships are really few and far between. And I think vegetation would have an effect. Certainly at Panola it does. This is in Georgia. It has wet winters and dry summers. When the leaves come on the trees in the spring, it's like a step shift in hydrologic behavior of the catchment. So vegetation does have a big effect. But it's tough to say it has this general effect because it does vary depending on the climate situation and so on.
These are all forested.
They're all forested catchments. Now, you can't equate this directly to a road, of course, because roads are like leaky dams often, and there is other complexities going on here. But I think this does indicate that there's maybe another way of coming at the problem, and I think it has to do with the fact that every road section seems unique because rarely do we have the number of storms to kind of define these relationships. That one site that I showed you for Panola back here, this site, that's about 150 events that we've been able to accumulate over 2 or 3 years. Most of the sites in the literature, ours included, are like, PhD students happy if she gets or he gets 4 storms, 3 storms. And this really shocked us because we'd worked in this kind of environment. In fact, I had 2 PhD students and 2 or 3 postdocs publish a lot of their papers on this kind of behavior. And we had about a 2-year hiatus where we continued collecting data, but we didn't do any intensive field experiments. And that's when this threshold appeared to us, and we thought, oh God, we really didn't understand this hill slope, and it's got us thinking about the thresholds and nonlinearities that exist elsewhere. And this is something that's really tough with the meager data that generally exists. Yeah.